Okay, good afternoon, everybody. Today I'm going to do a deep dive into the way that grid front ends work in YT. This is also going to talk a little bit about how chunking works in grids. I'm hoping to do some grid visitors work and maybe talk about why and how log spacing can work in YT. So, go ahead and get started. Let's put this on coding. All right. So, to start out with, the way that we've set up grids in YT is reasonably, um, let's say, at present, it doesn't do a whole lot of cleverness, and I know that is, sometimes a good thing and sometimes it's a bad thing. The reason that I bring that up is because one of the things that I'm hoping to address in the near-ish future is to make it a little bit cleverer so that, among other things, we can build out faster methods for data selection and so on. So I'm going to start up a new notebook. Let me go back here to my home directory. Let's create a new notebook, hide that window. We're going to call this the Pi39. Let me make sure that my YT build is up to date. Let's take a look at how grids get accessed. Oh, looks like I've got a whole lot of building to do before that can work. But the basic idea that we're going to start out with is we're going to look at how grids are stored, why they're stored the way that they are, and then how and why data is selected from them. So I'm going to open up a couple different files. This is the grid patch file. This is the grid geometry handler. Whenever we have a data set in YT, the data sets are designed to be reasonably lightweight objects. We aim to make them so that they can be instantiated very quickly, so that you can load up lots of them without reading any data off the disk, just getting the metadata about them. So among other things, that means getting, when was this created? When was, when were all these different simulations run? What are the parameters of the simulations? Where are they located on disk? And so on and so forth. What this ends up looking like, if we've got something like this, let me rename this to grid exploration. If we load a data set off of disk that is an adaptive mesh refinement data set, first loading, it doesn't really do very much. It just loads the metadata. And so that means it parses out stuff like the parameters and whatnot. And let's see if, and it doesn't usually find out the fields that are accessible. It's when the index is generated that a variety of different things are constructed. So a grid index has all these different attributes associated with it. So grid left edges. Oh, I always get the plural and singular mixed up. This is a unitful array that is n by 3, where each one is a grid left edge in the x, y, and z. Now if we look at, say, grid right edge, that's the right edge in x, y, and z. Now this doesn't tell us much unless we look at the grid levels, and for historical reasons the grid levels is shaped as 173 by 1 in this case, so there are 173 grids, and we shape it with an extra dimension, so it's a two-dimensional array. And I know that's a little bit frustrating in some ways, but that's how it is. And we also have things like the grid dimensions. And you'll see this is once again a two-dimensional array where the second dimension is 3 and the first dimension is n, where n is the number of grids. So when we access data, there are two different ways that we select the data. The first way is ensuring that whatever data container we construct we use that to figure out which data we are interested in. So if we have a sphere, we only select the data that's within that sphere. The second method, specifically for grid-based data sets, is that anywhere that more than one grid overlaps, and typically with ENSO data, with many types of mesh data, this is where you have higher resolution data overlapping lower resolution data. So you maybe have a better solution to your partial differential equations, ordinary differential equations, inside some given region, and you wipe out you utilize that in those regions. Occasionally, though, there are types of data where you have same resolution data that is mirrored across multiple different blocks. So maybe you have two different blocks of the same resolution that are overlapping somewhat. We also mask that data out. So this dual-step process of masking based on a selector and masking based on what we typically call child or sibling grids happens. It's because of this that the data often gets returned to us as flat. So if we do dd equals ds.allData, and then I access something like density, this comes back to us as a one-dimensional array. The shape of that array is, in this case, 3, 6, 4, 4, 4, 6, 0, which is not the same as grid dimensions. If we take the product along axis 1 and we sum that up, you'll see that that is actually 416, 0416. In fact, that's because we have masked out all of the data. So if we look at, for instance, ds.index.grids 0, we look at children, see that it has multiple different children. That grid also has a child mask associated with it, which for all the things that are visible here, it's true, but if we look at the sum versus the size, see that in fact many are masked out. So how do we do this? Well, we have to keep in mind a couple different pieces of information. The first of which is that we want to ensure that we are operating in as memory conservative a fashion as possible. So that means that we want to be able to possibly load all the data that we want, but not necessarily load all the data that we want in advance. Oftentimes we want to be able to do memory conservative operations. So in those cases we do what's called a chunk. So there are three different ways to chunk in YT. The first way is, let's say that we've got for chunk in dd.chunks. The first way is to chunk based on all. And that's what happens when we do something like dd density. It constructs a base chunk, which consists of all of the grids. It figures out how long that is going to be for the return to data. It allocates an array, and then it iterates through every single grid and puts the masked data in order in that grid. So if we were to do something like for chunk in dd.chunksAll, we can say print chunk density.size. You'll see there, it is just that one size. Now, the second way to do this is to do something like chunk in IO. And what IO does is it allows you to specify different heuristics for the way that you divide up your grids. So for instance, let's say that you're on a file system where opening a file and searching through it can be very expensive because you need to get file handles or things need to be loaded off of some tape with a robot going out and grabbing them or something like that. What we want to do is we want to allow the front ends to minimize the overhead associated with loading data off of disk, and so you can outsource that. So in this particular case, because we're dealing with an ENSO data set where you have multiple different files, each of which has grids in them, IO chunking, rather than sorting by the grid's number or location or whatever, IO chunking sorts them by which file they appear in, into the order that they appear in each file. So if we do this, we're going to see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that just so happens to correspond to, let's see, data YT sample data, isolated galaxy. That just so happens to correspond not to the number of files, but to the number of files with content in them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, the way that this particular data set was load balanced, a whole bunch of the files are empty. So there are 10 chunks out of 16 objects. And here, let's say that we wanted to do sum of chunk density dot size it comes out to be exactly the same. Now, here's the final way that you can chunk up data in YT, and that is through what's called spatial chunking. For chunk in dd.chunks spatial, what this does is, and you will see this has slightly different values than what you might be expecting, is this chunks it up so that you have spatially organized data. In each of these previous two chunking systems, the chunks that come out are flat arrays that represent the grid data that's been masked and then put into a flat array where you map basically the IJK into an n, or n increments as you go along. This one maps them out as spatial objects, and so within this loop, each density array will in fact be 3 dimensions, and if we do this, you'll see that this gives us one chunk for every single grid. And if we look at the shape of those grids, you'll see that they just so happen to match the dimensions. Maybe not in the same order, but they match the dimensions of all the grids above. And so here, if we were to do sum chunk density dot size for chunk in that, and you'll note that I'm doing size, not shape, we get 4160416, which is the same as the total number of grid dimensions. So here's the tricky part with all of these different chunkings, and we're going to ignore spatial chunking for now, because spatial chunking is typically done internally. It is almost never done by user-facing code. Oftentimes, spatial chunking is done in order to operate via stencils on objects. It is the result of those stencils that we then put into the one-dimensional array. So if we were to request something like dd.velocity divergence, internally this constructs a spatial chunking. It then takes all of the results of that spatial chunking. This is taking way longer than I would have expected. It takes the results of all that spatial chunking and stencil application and whatnot, and then it masks them with the child data again, and it fills them in order into a one-dimensional array, and you'll see that one-dimensional array is right there. So the reason that this becomes a little bit sticky when it comes down to things like I/O and so on, and grid visitors, which is what I'm going to get to in just a few minutes, is that we want to be able to have the ordering the same. So let's say that we have a momentum field. Let's say it's momentum x. All right. This momentum field is the product of our mass and our velocity, centimeters, grams per second. So we want to be as minimal as possible in the data that we store inside our objects, as well as the data that we load off of disk. So what we do is we want to ensure that all of these arrays, so that the XYZ position of this, the IJK inside the grid index of this, is the same regardless of our chunking mechanism. And that's where the I/O handlers get a little bit sticky. So what we need to do, if we look at something like the Enzo I/O, we have what's called a read fluid selection. Now, read fluid selection is not the best name for this, but the reason that it is the way that it is we need to be able to handle all of these different chunking mechanisms and systems. So read fluid selection is shorthand for read a set of values whose positions and thus whose inclusion inside a geometric selector can be determined by their IJK values or something like that. The distinction here is between reading continuous fields which are, have an XYZ, XYZ, and then some dimensionality, and they're assumed to fill the volume in between, and reading a set of discrete points like particles where they have an XYZ that is an intrinsic value associated with their like as a field on disk or something like that. So read fluid selection is a feature of essentially every single grid-based front end. And what it takes is it takes a list of chunks, and this is where actually there's some design decisions that were made a long time ago that don't quite hold up. Initially, I thought that when I started writing the YT 3.0 code nigh on a decade ago, I thought that chunks could just be a generator. Turns out, oftentimes you need to iterate over them multiple times, or exhaust them, or do random access, or something like that. So this didn't quite work out the way that I wanted, and in nearly every single front end, chunks is immediately converted to a list of chunks. So we now have a special case, in particular in the Enzo front end, that checks whether or not it's a grid selector. Now the reason for this is we have two different code paths that we can go down. We're going to ignore this one for right now because it's very Enzo specific, but the idea here is that if it's a grid selector, we only want to read one chunk. We don't need to apply a selector to it, and we just return it. That's the spatial chunking that I described earlier. Remember, when we looked at the spatial chunking, the grids were essentially provided as is. So if we were to do something like ds.index.grids 0 and access density, you'll see this object is selected with a grid selector. In fact, if I look at ds.index.grids and I look at, selector, it's a grid selector. This is a special case for when we have a non-geometric, where we're essentially selecting based on criteria that, the grid selection. So the second thing that we do inside this is we compute the size. Now, if we've been fed a size because perhaps we have run this routine before, this is the second time we're accessing a field or something like that, we know how big it is. And so we can just allocate it. Now, this is not the same as the shape of the field that we allocate. In all cases, in this particular case it is, but in some cases we'll have vertex-centered data or something like that that changes the story a little bit. So if we now look at this, we've now got our size, and this is computed by calling g.count on each selector. So this is where the grid patch comes in. Grid patch has, grid patch has this count operation. What this does is it gets a selection based on the selector. So if we're selecting from like a sphere or a cylinder or something like that, this selector object will be a sphere or a cylinder, and it computes the mask for it. If it doesn't intersect, the mask will be none, and the number of cells included are 0. Otherwise, we return this last count. Now this is where things get a little bit sticky, and this is often not code that is visible to the front-end implementers. But because this can be a very expensive operation, we want to cache it as aggressively as possible. And it looks like I missed get selector mask. Where is it defined? There we go. So, and I realize you probably can't see that. So what this routine does is it receives self and selector, and if we're allowing ourselves to cache it, and it turns out that the most recent thing we asked for on this grid was that same selector, then just return the last mask that you got. Otherwise, make ourselves a new mask and cache it if you need to, and make this ID the way that it is, and all of that. So essentially the reason that we're doing this is because in particular situations, we can find that calling this getSelectorMask function and computing which parts of this grid intersect with this can be very expensive. We want to save ourselves as much as possible. So we figure out how much we get, and we just count that all up. Okay, so let's go back to our io.py. So we sum up the counts. That gives us how big our final array is going to be. And here we do a little bit of dancing around in order to pre-allocate our destination for our arrays. This is another thing that back when I was thinking about it, I thought, oh, you know what? It's always expensive to allocate arrays, a whole bunch of little arrays, and then concatenate those arrays, because then you've got this big overhead of lots of little arrays and making a big one and filling them in. And it turns out that in most cases, that's not really most of the cases. It's not that big of a deal. And in fact, as we've moved away from doing things like accessing all of the data all simultaneously and made it a lot easier to do piecewise reductions and whatnot, I think that it's no longer really that relevant to do it that way. But we pre-allocate all of our fields, and we then compute the number of grids that we have. That's mostly for debugging purposes. Now finally, we've got all of our arrays allocated. We need to track where we are so that as we're filling, we, let's say that we've got a grid and a big chunk of it is selected and a chunk of it's not. We iterate over and then we fill, incrementing our position in both the grid that we're filling from and our destination file. So we start at 0. This is going to be our index into our RV, which stands for return value, not recreational vehicle. And we iterate over every single chunk. For Enzo data, this will be files. For Flash data, for instance, this will be subsets of grids in files. So for instance, we may set up chunks for Flash that, we never read more than 64 cubed cells at once, or whatever. So we iterate over the chunks. We iterate over each grid in each chunk. And we then do for field in fields. And here we do a little bit of HDF5 magic, if you will, where we say, here's the view into our data. We're going to swap. Oh, this is all in-memory data. Let me pull up our, I went to the wrong spot here. Oh, yeah. So we do that. I'll just keep going here. We then look into our data, we copy it, and then this g.select, once again, much like what we had seen before for the counting, it goes into Cython code, takes our selector, takes our source, takes our destination, takes our current position in our destination, and then it copies the data one by one, and then it tells us how many data values were copied. So in doing this, we're now filling each object in. And remember, for an all chunk, this will be just one item, and we'll have all the grids. For an IO chunk, this will be individual files, for instance, or subsets of files, and this will be just those grids that are included in those. And then for spatial chunking, we'll never even get here because we're just going through this. So if we now look at, say, a little bit more general in, let's see. I'm going to pull up. And I'm going to put the, so, that's exactly what we looked through. So, for things like big unigrid simulations, because unless you construct some type of a virtual grid or something like that, there's only going to be one grid and there's only going to be one file, it becomes a little bit trickier to do anything like chunking unless you do construct some type of a file or some type of a sub virtual grid on it. So one way that you could do that would be to construct multiple grids that correspond to different subsets of the domain. In essence, this is what the stream front end does. We've got this, let's see, where is it called? Is it loaders.py? One moment, let me figure this out. Load uniform grid. So what the stream front end does is it accepts this nprox argument, which really is more like a virtual, number of virtual fields. And what it does is it says, okay, how many processors do you want to decompose this across, or really how many virtual grids do you want to construct? And then what it does is it constructs a new set of left edges, right edges, shapes, and slices by calling decompose array. And then it sets that as the grid dimensions. So in principle, what you could be doing with respect to, say, a big uniform grid front end is in your I/O. Instead, here, if you're selecting a grid, each grid could have an attribute that describes its left edge in the domain, which actually all grids do have in integer position. So ds.index.grids, let's do 45. Get global start index gives you an integer position of the left edge of that grid with respect to its resolution level. So in a uniform grid, all of these would then be the same. So you could use that information here when you are reading data off of disk in order to read a subset of, say, the HDF5 data. Because you can do something like, if you've got an H5 data set, you could say H5 field name, and then here, say gi equals ds.index.grids 45, get global start index, ge equals gi plus ds.index.grids 45 plus dot active dimensions. And I can't, do we want a +1 or not? I don't remember. Then you would just say gi 0 to ge 0, gi 0 to ge 0. Oh, these need to be 1s. gi 2 to ge 2. And this would do it for you. So essentially you would be constructing virtual grids using this get psize function, which takes an input shape, the number of things to divide it across, and then you would do decompose array on it, and then it would give you a set of grid left edges, right edges, shapes, slices, all that stuff. And in fact, these slices could just go right onto these slices would be could just be attributes of the grid objects themselves, and you could access those. Okay. All right. So let's see, where do we go from there? So that's basically how chunking works for grids and why chunking works the way that it does. Now I'm going to talk a little bit about how I want to see it improved. Because what you'll notice here is that a lot of this stuff, like io.py and all that stuff, a lot of this relies on things like doing a whole bunch of masking and copying of arrays. And there's no intelligence to it in the sense that if we know that grid B is fully contained within grid A, and we know that grid A is not selected by this geometric selector, we should not also evaluate if grid B is selected by that. There are a whole bunch of caveats to that, mostly related to what I had described earlier about sometimes they'll be overlapping, sometimes they're not fully contained, and so on and so forth. And additionally, depending on whether you're doing selection based on cell centers or cell edges, it can get a little bit confusing too. But there is a more intelligent way to do this. So I'm going to briefly digress into talking about octrees, because octrees are a really fun recursive data structure. And the way that we handle octrees in YT is using an oct container, which is either sparse or non-sparse. And in the sparse case, it has a root grid that is only allocated when you've actually got something there, and in the non-sparse case, it allocates everywhere. But what we do in order to select things in it is we do what's called an oct visitor. And so what an oct visitor does is it's a tiny little itty bitty function, and you can see most of them, most of the functions that they rely upon here inside octvisitors.pxd. But what oct visitors do is they take an input array, an output array, and information about whether or not a cell is selected, and then a little bit of data about where the visitor is in each position. So you can think about this as a simultaneous traversal of our output array and our set of input arrays. But instead of doing all the selection and then copying the data, here we read all the data that we need to, and we subchunk this and whatnot, and then we do a simultaneous selection and copying of the data from the input array to the output array. This lets us do things much more memory efficiently, and it also lets us do things a bit faster because we're not dealing with a whole bunch of gigantic arrays anymore. We've reduced the amount of data that we're reading or writing and then throwing away immediately because we're not storing masks and whatnot. So the way that it's set up is we have these oct visitor classes, and a base oct visitor class has a bunch of information about where we are. It has information about the octree itself, so the number of zones inside a given cell, whether it's Fortran ordered or C ordered, our current position in along the XYZ axes in integers, and on and on. But it's a reasonably minimal set of data. And then we define a visit function. And what the visit function does is it copies data from one place to the other. And so in this case, we've got this copy array I64. This copies an integer 64 array. We've got a copy array F64, and we might be able to do these with fused types inside Cython, but I'm not sure, and additionally, I don't know that it would actually assist us that much. But we can also do stuff like set up our coordinates. So for instance, we can have an output coordinate of our integer index, where instead of having to generate a whole bunch of math operations all at once at the top level, which granted could potentially take advantage of SIMD operations and whatnot, we generate them as needed as we iterate through the array. And you can see that rather than generating many things in advance, we generate them on demand. Same thing for iRes and for fchords and so on. The way we do stuff for grids is very different. We do a lot of pre-allocation of masks and of positions and so on. And it would be really nice if instead of doing that, we could do something similar here, where we are allocating things as we go and as needed. And so that's where grid visitors come in. So the grid visitors pull request is one that has been around for quite some time, and I'm going to use this opportunity to refamiliarize myself with some aspects of it, but parts of it have already been included into YT proper. So let's take a look at our grid geometry handler. So if we look at and let me mark this as markdown. Okay. So if we look at ds.index.getGridTree, this gives us a Cython object called the grid tree. This grid tree object, and I believe the grid tree is all defined. I guess inside grid container. What this is it is a Cython object that includes a bunch of grid objects inside it. Now, normally we've got all of our grid objects here, ds.index grids, and we get all these different things from it. In this particular case, we are, and each one of these is a full Python object. Is it possible to get size of Python object? Probably not. I feel like there may be some issues with this that, like maybe it's properties, if they're views and whatnot, might not get counted correctly, but we can take a look. Yeah, all right. So in bytes, this is 48 bytes. So that's quite a bit of overhead, plus all of the different arrays that it references inside it. And additionally, there's one thing that just bugs the heck out of me. Yeah, thank you. I see. Nope, you were probably fine. I was just in I just had a different window open, so I didn't see it. It's that if we look at something like ds.index.grids 0.childmask, this is a uint8 array, which means even though it's a 1-bit item, it's actually 1 byte for every single item. And now that brings us some good stuff. It brings us the ability to access it randomly and provide views and whatnot. But it also means that our child masks are about 8 times bigger than they necessarily need to be. And so if we are masking a big array, it can get quite expensive. Now we instead can pack our data into bit arrays. And I've got a bit array function that I wrote one, and then we've got a much better one that Megan Lang wrote a wrapper for and then expanded and developed. But we should be using one of those instead, since none of this is actual user-facing. It's all used internally, for instance. So when we construct a grid tree, what it does is it sets up a bunch of child pointers, and it sets up zeros to those. It constructs the number of grids, root grids, leaf grids, and so on. And then it initializes each one from our left edges and right edges that are parsed and owned by our hierarchy object. Now this means that if we, here let me assign this, tree equals that. There aren't a lot of user-facing functions on the, oops, I got a new keyboard and occasionally I will hit the button that switches it to a different thing. You'll see that it's got stuff like count, grid arrays, mask, return tree info, select f chord, select f width, and so on. I think return tree info is an interesting one because here it returns to me a tuple where you'll note that each one of these corresponds directly to an array, but to one of the arrays. But the neat thing about this is that it's done, but oh no, it's not done the way that I thought it was at all. Oh yeah, it's grid arrays, that's what it is. So if I look at tree.grid arrays, this is an array that is a wrapper around a view onto our grid tree node objects. So the neat thing about this, and I don't remember what this is. Oh yeah, okay, well, whatever. That's all about nested D types. That means that we've got a view onto a bunch of C structs. You can even see here's some fun uninitialized memory, or maybe that's 32, 64, getting confused or something like that. But the long-term goal here is, because we assert, and we have some evidence to support this, that doing our operations in Cython, similar to how we do them for the octtree, can take advantage of conditionals inside tight loops, can take advantage of much more packed data structures and packed arrays. And because we can we can take advantage of locality information. We can take advantage of locality information. So for instance, we can take advantage of knowing that if a grid is fully contained within another, and that other one is not a part of our selection, then we don't care about the child grids. That becomes really, really useful. So you'll see that this mimics much of what we saw in the octree setup, where we've got visiting of grids, recursively visiting grids, counting, and so on. But you'll see that here we're using a bit array as a mask. We're using a visit that will skip over if need be, and whatnot, in order to get our size. And let's actually, I kind of want to know what the state of this is. So let's do tree.count dd.selector. Is that, yeah. This might even segfault for me. No, it gives me the right answer. So that's what we get. So we can start to utilize this. There are a couple downsides to this. One of them is that if we move exclusively to this, it will require that we construct grids on demand when we want to access the data inside a single grid. That's probably okay. We can do that. It means that we're going to be moving more code into Cython, which is sometimes a little bit frustrating, but is not necessarily the worst thing in the world. And it also means that we should be able to change the way that we think about grids. So currently we think about grids as big collections of data that are spatially organized and whatnot, but for the most part we only interact with them as though they are flat arrays or sets of arrays or something like that. Chris Haviland has been working on implementing Dask operations inside YT, and it turns out that the situations where we are able to quickly apply indices, like with particles and octrees, lend themselves much more to immediate, let's see, what did we call it, the daskening? Yeah, they lend themselves much more to daskening than some of the other ones do. So we can assert that we want grid visitors to operate. Now here's where some of the trouble comes in. When we start using grid visitors, there are different chunking systems, and it turns out that depending on how we do our chunking, the grid visitors that skip around inside of our arrays don't necessarily encounter values in the same order. So what that means is that if, for instance, we were to access cell mass here, and then we were to do dd.chunks, and we were to access velocity x for chunk in dd.chunks x, and we were to say, start up here, ind equals 0, dd dot velocity x times dd cell mass ind to ind plus dd velocity x dot size, and output equals that. output.append that. Now, the way that it currently stands, yt.uconcatenate output, this should be the same as but if we now sort of suspect that the return order of these chunks is not the same, that will no longer be the case. So for instance, if we were to say for chunk in reversed dd.chunks, well, whatever, we can't do that because of the way that it sets up. But oh, I know what we can do. We could say output dot insert 0. Oh, insert 0 -1. No, is it push? Anyway, it shouldn't actually. Oh, yeah, because end equals end plus 1. Well, I'm obviously doing something wrong, but if we put the chunking out of order, then it will no longer be independent of our chunking style. So we assert that index I of a data object, whether that data object was constructed via chunking spatial, IO, or all, index I corresponds to the same cell. And if we don't rely upon that, then it will not be true. So the whole point of the grid visitors, and the reason that it's stuck right now, the point of the grid visitors is to speed things up. And the reason that it's stuck is that right now I'm running into some conceptual difficulties with how do we manage early termination due to recursion, giving us things out of order. That's a little bit tricky, and it's where I want to move towards next. Okay, so the last thing that I wanted to check out today, let's see. What did I call it? I guess I don't know. Let's take a look at my branches and see which one it is. I can't remember what the name of the branch was where I started looking at log spacing. Let's see. I should really delete some. Ah, yes. There we go. Okay, so this is the pull request, and it's in draft and probably needs to be rebased at this point because it was from December of 2020, which feels like it wasn't that long ago, but is. And the idea here is that what we want to be able to do is we want to be able to have grids that are spaced irregularly along axes. So right now, each grid is uniform. Each little checkerboard square or rectangle is the same size and orientation as all of the others. We want to make it so that they don't necessarily have to be. This comes in handy when you're doing something where, say, for instance, having resolution along the radius of a simulation or something like that is better suited towards logarithmic spacing. So the way that we handle this is right now we don't. So what we want to do is we want to make it so that we can. I've started work on this by looking at how we can separate out regular grids from irregular grids. And I started that by constructing this fill mask regular grid, and then for other situations, having a general fill mask object. Now, this gets a little bit sticky because we want to minimize the changes to what has come before. But if we look at, say, g equals ds.index.grids 0, all these grids have a DDS array associated with them. This DDS array is of shape 3, not 3, 1, not NMX or anything like that. It's an array of shape 3. This is tricky. For situations where we have irregularly spaced grids, what we really want is we want this to be number of X cells long, number of Y cells long, and number of Z cells long. So for a grid like this one, I don't know what that was, it would be fine. If we were to look at, say, ds.index.grids 45.active dimensions, let's try 47. Yeah, this one would be hard. You can't construct a NumPy array that's ragged in this form. Grid 47 is 34 by 4 by 26. So we can't really have a DDS array where it's two-dimensional, but the first dimension only has 34, the second one only has 4, and the third one has 26. That's not something that NumPy supports. There are libraries out there that do support it, but relying on them can be a little bit hard, just because they move very quickly in some ways, and YT is more slow-moving in others, and it just gets a little bit sticky. So let's take a look at what I started looking at, which was the idea that we have a fill mask selector object, where it assumes that each DDS is in fact an array. This is helpful to us because we can mock up the process. And let me pull. Where is the code where I did that? Oh, actually, you know what? It turns out that I took a much simpler approach to this, which was that for the most part, I did not address the real problem, which was the DDS attribute. Let's see, this is a whole bunch of conversation between me and Clement. But the basic idea here is if we can get things sorted out so that we start assuming that some grids will have DDS arrays, not all grids, but some. We can then set it up so that we pass in semi-variable DDSs to all of the other objects. That will be the first step. The first step is utilizing more intelligent methods for storing our cell sizes. And then the second step is going to be a little bit harder. Where John Zahone and I have always gotten stuck in the past has actually been in a really fun place, which is the pixelization routines. So by default, what YT does is it constructs a pixelization in Cartesian space, in linear space. In logarithmic space, this becomes a little bit trickier because you run into the situation that you may have weird round-off errors and things like that that propagate across your cells. But I think I'm kind of talking myself into this not being quite as difficult as I had thought. So why don't I have a go at rebasing this, having it run, and seeing where we need to go from there. So let's take a look at this. I'm not good at rebasing. I wonder if there's a thing that I can use to help here. Let's see. Is there... branch. Rebase branch. Rebase onto main. Where are the conflicts? Fill mask selector. Thank you. I'm doing it with the GUI though. What did we change here? Left edge, right edge, DDS, dim, uint8 and dim, cast equals true child mask. Mask int level. I think that's what I needed to do. So let me go back up here. And make sure that I didn't get rid of anything. Aha! That's what it was. Pass this up here, fill mask selector, regular grid, but then the second one, we got rid of the DDS3 and made it a star star, so. Okay, I think that'll do it. Let me make sure this compiles. What's madness? Oh. Let's see. Fill mask selector is declared but not defined. What? Oh, rebasing in a GUI. Yeah, well. Yeah, it's there. Why is selector object.pxi? Let's take a look. Yeah, this did not turn out the way that I wanted it to. I am going to abort this. Okay. So instead, I'm going to do this on a command line, like I probably should have. Yeah. I'm going to merge it. So merging worked, rebasing did not. I can rebase it later, I suppose. Maybe it was all just the, maybe it was the VS Code helper function causing problems. I don't know. Okay. Let's see if actually I probably should have checked if it compiled first, huh? Yeah, looks like it's compiling. All right, well, now we'll get notes back about whether or not it passed the GitHub Actions, but I think I've now convinced myself this might be reasonable to do in the near future. I think what we can probably do is we can stage our way into it. Start by making things work in the more general case, little bit by little bit, and then start expanding it to work in the cases that we're interested in, where we actually do have grids with those DDSs. The next step forward is going to be taking a semi-structured grid and trying to make it work with the normal grid objects. We should then see a vast speed up in performance. So I think that has been what I can do for today, and I think this has been a reasonably productive streaming session. I am going to try to revisit this in the very near future, but I think for now, time to sign off. Thanks, everyone.